So I will continue with the last test case that I prepared for today. And this will use the results that we did before for the command line setup with VMD. And it will use together with the Gaussian software, right? So if you go to MDQM, NumD, and Gaussian folder, you will find the relevant files. So this is the part that we did today in the morning. And we will use some of the files from this simulation. So I will change to that directory. And then I have already loaded the modules for VMD and VMD itself. And here, this is the first point. In general, it's not possible to get a good equilibrated structure in such a short time as we did before, just with a few steps. And then I equilibrated the structure previously, and I put the files in the folder, and they are called the 4A ion EQ, PSF, and the PDB files. And the basic vectors are these ones with the cell origin at this point, right? So you also made the calculations consistent. But if you want to do a realistic system, you can run your simulation for a longer time and then get your own structures and use the information that you get. Specifically, how to get, this is something that I didn't know before, how to get these values here. You can take a look at the XSCS file from VMD, and it will tell you what are the lattice vectors that were used in the final step, for instance. So you can copy and paste that, and this is the origin at the end. So let me go to the configuration file, and this is called for AKE, equilibration, QMM, and configuration. And here we need to write the name of the PS file, PSF file, and here is the name of the PDB file. These are the parameters that we used previously. And the lattice vectors for this particular structure are as follows: 56, 85, 74, 16, and 70.59. and the vectors. Yeah. These parameters are similar to what we see before for NAMD. And here we start with the QM part. Here we start with the QM calculation, which is set to on. And this is a file that will be used as a reference, as I mentioned before. In the beta column, we will indicate what atoms are the one treated quantum mechanically. And we will do it right now. So I will open this file for AKE ion un.pdb. And here, if you don't know how the columns of the PDB file are labeled, then you can go to this website, and that will tell you what are the names of the columns. Yeah. And for the beta, let me go to this. So it says the fields seen here in order from left to right are the atom ID, this one, the atom, no. This is the atom ID, the atom name here, the residue ID. These are the X, Y, Z positions. This is the occupancy, and this is the beta factor, also called the temperature factor. Here it says, replace the value of 0 to 1 for atoms in the beta column. So the beta column should be here, this one. And the atoms, this one, in the beta column from 0 to 1. And from 1878 to 1895. And if you look at the values, they correspond to the entire arginine. So I will include one arginine into the QMM region. So now the value is set to 1. And this will be treated quantum mechanically, right? And the boundary atoms, for the boundary atoms, we use the occupancy column, which is this one. And we will replace the value 0 to 1 for the atoms 1876 and 1878. So the bond will be broken at the level of the C alpha and C beta boundary atoms. So all the atoms in the residue in the side chain will be included. Yeah. And this is something that you also need to consider depending on the package, because I mentioned before, if the charges doesn't add to some integer value, then you can get some error from NumD because it does accept only integer values. And that's why I had to include all the atoms in the residue for this example. So, okay, I have fixed this file. Then, if we look at the config file, and we go further, you will see here a script that is used to run Gaussian. Yeah. And this is called run Gaussian.py. This is a Python script. This will look like the following script. Basically, it's Python. And in this part, notice that I have some instructions for the Gaussian input file. Specifically, we will use Gaussian 16. And because of that, you need some line to tell Gaussian what are the CPUs and the number of CPUs to be used. Also, if you want to write some checkpoint file, the size of the memory, and some specific lines for the type of calculation. In this case, is B3 the standard one. With this basis set, we will do the charge and force calculation. And these lines are used to set the standard 2009 set of constants, right? So if you don't set that in Gaussian 16, then you will see that the program runs slower. And that's why, and that's because they needed to increase the finite grid accuracy in Gaussian 16 because it was meant to run on GPUs. The other instructions are for the multiplicity and the charge. And here, basically, you don't have to modify anything from this Python script. So here is the path to where Gaussian is installed on Kebnekaise. But as I said, you don't need to modify this script unless you want something more specific from Gaussian. So this is the driver script. And we come back to the configuration file. So in the QMM exec path, right, you need to fix it to the path to where this Gaussian, run Gaussian script is. And in particular, for this case, I know that the script is located here. But this path will depend on the username that you are working on. So, okay. So also the part where it says QMM base there need to be modified accordingly. And this will be the path, but without the run Gaussian script. Should look like this. And we will be running 5 minimization steps and 10 steps for the real simulation. Okay, we are done with this file. Then we can use the NAMD QMM script. And here we write the project name for the present course. Together with the reservation. And notice here how I load the modules. I need to load Gaussian, the modules for NAMD, MPI version, and some compatible Python version. If you use Python 3, you will need to change the run Python script. Okay, so we are done with this part. And I can submit the script. So it's running. I will check again how my simulation is performing. This is still running, which means that NAMD is running. So I can check the script for NAMD, which is written in this log file. And it gives me information about the quantum mechanical part and also the MM part, right? So if you look at the log file, you will see all the relevant information for the quantum mechanical region in this section here. So it will tell you, for instance, the size of the QMM region, number of angles, dihedrals. And here, for instance, it tells you number of atoms, 18, and 1 QMM bond was found, right? So when you run the simulation, you will see a new directory called 0, which contains the output files for the QMM part only that is solved by Gaussian. So the output file of Gaussian, it's here. And it's telling you how the simulation is progressing. So in particular, when it goes into the self-consistent field calculation, then you can see that here, and also the final result, if that converges well. So here you can see the input file that Gaussian is using. And you can see that 4 cores are used for the present calculation. It's running, it's writing a checkpoint file using this amount of memory with this option for the quantum mechanical method. And this is the structure that is being used. And the classical atoms that are included to polarize the quantum mechanical region. So this is a good output, I would say, because once you have this output, it's like if you were running Gaussian or Orca just for that set of atoms in the QMM region. So all the simulations or the post analysis that you can do with Gaussian, you can do with all these files, including, for instance, you can visualize the HOMO, LUMO, and all this set of analysis commonly used in Gaussian. As you can see here, this is how the resources are being used in the present simulation. And it's still running. Okay, is there any questions at this point? Any comment? So it finished just with the 15 steps. So I strongly recommend to use this tool here, obtained from the job usage command, because for this type of simulations, we are adding some layer of complexity to the classical MD simulations, right? And it's common that, for instance, in the batch script, one could set this number to, for instance, 56, but finally you forget to update this value or update the value in the configuration script for running Gaussian. And from the 56, you end up using just 4 cores, right? and then you reserve 2 full nodes, but you're using part of one node only. So this will tell you some information on how to run your code more efficiently, especially when you combine different software. Is there any questions, comments? Regarding the question of setting up a non-cubic box, up to this point, I haven't found an option to set it with the tools that we saw today, either on the command line with TK in VMD, or with the quick MD. So quick MD seems to be constrained to the cubic box only. And the plugin on the command line, which is called Solvate, seems to work only with cubic boxes. But if you have any further information, just share that with me. Also, for instance, as I mentioned before, here in the Gaussian results, you can find all the relevant files for post-analysis of the simulation. So there is a tool called Gauss View, which is not supported at HPC2N, but it is supported at other SNIC centers. And with that tool, you can post process the output files from Gaussian, right? There is another tool called Avogadro, where you can also post-process the information from Gaussian, including, for instance, the Homo Lumu calculations. Are there any questions?